yet another module that I'm very excited to share with you today. This is going to be on distributions, CLT intuition, and p-values. So by the end of this module, you should be able to distinguish between a data distribution, a population distribution, and a sampling distribution. These are three different concepts. You ought to be able to explain, in high-level terms, the Central Limit Theorem, I called CLT a moment ago, in plain language and visualize it in Python simulations. You should be able to define and compute a p-value for a simple test using a stimulation or standard distributions. Actually, standard distributions have been taken out for simplicity, but there's some links later on. You ought to be able to interpret p-values correctly in context and identify common problems that people run into and connect p-values and sampling distributions to how we make decisions, which again is one of the main purposes of this course. So again, this is one of the main outcomes of this module is the three kinds of distributions. The population distribution is generally defined as an usually unknown distribution of some variable for all individuals in a population. So, usually when you hear statistics gathered, trying to estimate what the average opinion is of the average Canadian, there's not a sample of every single Canadian, there's only subsamples of Canadians. So we don't know the actual true population distribution, but there must be one, it's out there, it's just unknown to us. We do have a data sample distribution. So this is normally when we see a histogram or some kind of density function. This is the sample we've actually collected. So we've gone out to do a survey. We've asked people on a scale of 1 to 5, how do you feel about this thing? We have then a distribution over the 1s and the 2s and the 3s over however many Canadians we've surveyed. Finally, we have the sampling distribution of a statistic. This is a bit more nuanced and maybe harder to understand. But this is the idea of the distribution that we'd get if we repeated the study many, many times. And every time we did, we collected a new sample. And every time we got a new sample, we computed the same kind of statistic, but the actual value will change every time. So, for example, we instead of collecting one survey of Canadians, we've collected 1,000 surveys of Canadians. And in each survey, we have different averages, different means for those surveys. And over those 1,000 surveys, we can compare all of those means. This is deeply connected to the idea of bootstrapping, which we've seen in a recent module. So when we're doing inference, when we're trying to make predictions about the world, this is often in terms of three, right? In terms of the third kind of distribution. Like how does our statistic vary across imaginary repeated samples? This is going to be a theme in the machine learning section of this course, but the idea is we have some collected data. We have maybe a bunch of different batches or subsets of the data, and we want to use statistics in that data to make predictions about the world and to make smart claims about how the world works. This is what I just said kind of visually. There's a little bit of misalignment here at the bottom, but I'll just talk through it. So here's our population distribution. So this is something we don't actually see. Like this blue histogram is like the way the true population works. There's a mean value here of the tip percentage, around 18% it looks like. And then we have, this is the density function. We don't have access to the true population distribution in terms of how people tip after they've had a meal or after they've received some service. What we do have is a sample. So instead of having millions and millions of people, we have a sample of 200 people, n equals 200. And we have the tip percentage of all of the receipts we have in our sample. So we have 200 receipts, we have a tip percentage in each of them. We can compute a distribution, and it looks like this in orange. The orange distribution, in some sense, superficially looks kind of similar to the true population distribution, but it's not exactly correct, right? It's a bit lumpier, it's not as smooth, there's some gaps. So it's an approximation of the population. Maybe it's a good approximation, maybe it isn't, but that's yet to be seen. And then the third type of distribution is the one we're increasingly interested in. Again, going back to bootstrapping, instead of taking one sample, we've taken many samples. Here, many is 30, so we have 30 samples of 200 receipts. In each of those samples, we have a key statistic we're measuring. In this case, it's the mean. And then finally, we just say, like, what is the mean of the means? and it looks like it's over here in the dashed line. Again, somewhere between 14% and 15%, it looks like. Okay. You'll also notice that the shape of the sampling distribution here in green is not exactly the same as the others. The others seem to be shifted a little bit towards the left, whereas the green distribution seems a lot more like our standard bell curve, our standard normal distribution. Here's kind of how we gather the sampling distribution over more and more samples. So again, here's our population distribution. It's nice and smooth. It's a little bit tilted towards the left. This is like a good representation of the true tipping behavior of Canadians. I can just jump ahead a little bit. So we've gathered 50 entire samples. So this is a lot of samples we're going to be doing. So we've gathered 50 samples. Each sample has like 200 receipts in them. And then in each of those samples, we've computed the mean values, and then we're looking at the mean values of all of those samples. So this is like these are the means here, just shown in orange. So here we've collected 50 samples, looked at the means. About 6 times the mean is in this first little bar over here, towards the left. About 16 times the mean is in this next bar, and so on. I'm just going to play to the end. So we're gathering like many samples at this point, many more than we tend to have, up to 2,000. So we've taken 2,000 samples. Every sample will have many receipts in it. Every sample we can compute the mean, and then we just like take all the means and show their distribution. Again, this is the mean tip across each of the samples. And now we can see that the mean of the means is somewhere here in this big spike in the middle. Okay. This is still pretty coarse. There aren't too many bars here, but you can kind of see, just like the simulated example before, that the distribution is more symmetrical. Okay, the distribution of means is a bit more normally distributed than our original sample distribution, or the population distribution, indeed. So again, the statistic is a number that we compute from data. We've been looking at the sample mean really exclusively, but this could be other things like the difference in group means, like how different is this group versus that group on average. We can measure proportions, we can measure standard deviations. There's things called kurtosis and skewness. There's tons of stats we could pull out of a particular sample of data. A parameter is a number that describes the population. This can be, in this case, the true mean, the true difference, the true proportion. We're going to redefine parameters a little bit later in the machine learning section, but for now, this works. And then we have the sampling distribution of a statistic. So how that statistic would vary across hypothetical repeated samples from the same population. Okay, so this is related again to that third category of distribution. Like we've gathered many samples. Now imagine we have a model now in our minds, and we want to deploy the model, and we want to estimate, like, what do I expect the mean to be in the future for some other new sample of 200 receipts that I've never seen before in deployment. This is the sampling distribution that would allow us to make kind of intelligent claims about what do we expect to see in the future. So the key result here is that for many populations, and if we do a large enough samples, the sampling distribution of the mean will be roughly bell-shaped, as we've seen, and it'll get narrower and narrower, to some limit. Okay, so the like here on the right, or here again on the right, the sampling distribution of a statistic in the mean will become more and more normal shaped the more samples we have, and the more samples we have. So very briefly, the Central Limit Theorem is the idea that if you have n independent draws or samples from the same population, again, a sample is a collection of data, like a survey over many people, even if the original data is not normal, like in the two examples we saw previously, this distribution on the left is not normal. It's like too tilted to be really a normal distribution. But it still has a mean. So like even though that distribution is like tilted, it still has a mean, mu, which is the population mean. It still has some kind of standard deviation, which we could still compute. Then for a big enough n, the sampling distribution of the sample mean So at every sample, we compute the mean. We call that x bar because this is not the population mean. This is only the mean of this sample. This sampling distribution is the distribution we'd get by repeating the sampling many, many times. Again, I've mentioned this already. I'm just hammering home the same thing I've already mentioned. Then this sampling distribution will be approximately normal. I said this already also, but the sampling distribution will be more or less bell-shaped and symmetrical. Its center, mu, will be, its center will be mu. It'll be very close to the population mean. And its standard deviation will be the true population standard deviation divided by root n. This is getting to the point where I'm not expecting you to memorize this. I shouldn't say that, but this is something that normally is not super important to remember, nor is this equation. So the the difference in between a sample mean x bar and the population mean mu divided by this standard deviation of the sampling distribution will approximately be normal with mean 0 and standard deviation 1. This is very similar to what we were talking about before with the Z scaling or Z standardization. The equation's almost the same thing. Essentially here at the numerator, we're just taking the difference between sampling mean and the population mean, and that's what gives us the this 0 mean in this fictional Gaussian I'm talking about. But like I said a moment ago, I think I'm in the weeds a little bit, and we can just pop out of this description. Unless, of course, you care deeply about this, in which case I'm more than happy to walk you through it. So this approximation is about the distribution of the mean x bar across many samples. This is not about the original data being normal. Okay, I make that absolutely clear. CLT is sometimes discussed as if, like, well, if you keep on collecting data from any population, that data will eventually be Gaussian. And if unfortunately, like often in various other sciences, I'm not going to mention them, but other sciences, they'll often just assume that any measure we get from a population is itself Gaussian. I hope I haven't fallen into that trap myself, but I'm sure I have in a statistical test, which I'll talk about later. But yeah, the population doesn't have to be Gaussian, right? Like in this population on the left in blue, it's not Gaussian, it's not normal, it's too tilted to the left. People shouldn't just assume that that distributions are normal at the population level, even if you have a huge sample. That just isn't true. Why does this matter? This gives us a simple approximate model of how the sample means will vary. So this is going to get to the next big part of this lecture. We have a bunch of samples, and we imagine taking a sample in the future, and we imagine taking a mean in that sample in the future. And we're also going to see a particular result, and we want to see whether or not this result will be extreme, given, rare, given what I already know. Okay, so this will form the basis of, it'll build off of what we talked about in terms of confidence intervals. So in a recent module, we talked about, the confidence interval between certain percentiles, like 95% of the data will fall within this region. So if a certain observation falls outside of that region, it seems a little bit like something we might call an outlier. This idea will also form the underpinning of things called t-tests and z-tests, which we won't really get into here, but I just wanted to flag it because these are extremely common. And also, p-value land is what I call just like the realm of scientific inquiry papers where people are just trying to get very small p-values. I'll describe why they want to have small p-values in a moment, but it's both motivated and can be a trap for your scientific process to end up, not doing the right thing. I'll talk about that in a second. So the idea here is we're going to replace the idea of taking an imaginary infinite repetition with calculations on a normal distribution, and we can also take simulations, and then we can describe events relative to that normal distribution. So here's a bad thing. So again, I mentioned this a moment ago. Sometimes people say if I've taken a large enough sample, the Central Limit Theorem will say that everything is fine, and I have my Gaussian distribution in my sampling distribution, and I don't need to care about the skewness, like the tilt or the dependence or measurement bias or anything else. I've done this extra step. I've gotten my Gaussian sampling distribution, and I'm done. That's shortcutting around problems. The CLT normally talks about like the mean, and you might say something about the mean of the means across a bunch of samples, but it doesn't describe other statistics. It doesn't fix problems of biased sampling. So if all of your surveys that you've taken are biased in some way, the result is going to be biased also, and that's going to just be inherited by whatever your CLT distribution looks like. If there's measurement errors, this doesn't solve anything. If there's confounds or causal issues will be the subject of a subsequent module. CLT won't fix those problems. And yeah, basically, if you have biased, the main thing is you have biased data, then you'll draw the wrong conclusions. So this is something we keep coming back to, but it keeps on popping up in different situations like this one. CLT, so everything else here is not magic. So again, we've kind of went through this already, so I don't need to spend much time on it. The sample mean is just the, like we know the sample mean, the expected value is like computed over like using these sample means. This is the population mu, and then the variance is going to be sigma squared divided by n, the total number of samples we've taken. Okay, so again, x sub 1, x sub 2, x sub 3 are kind of like independent bootstrapping iterations, different samples. So nothing we don't know here already, but I wanted to include it anyway. Let's see some examples. So we're getting more into Seaborn now. Like Seaborn is a visualization library in Python, but it does some other things, like it includes data sets. We've already seen the tips data set, so just for continuity, we'll see it again. Nothing much is happening here. We're just loading the data and then taking the percentages and then showing it, or showing the first few rows of this data set. So we have the bill, the tip, and the percentage. And that's all it is. We know this already. There's some population of all the restaurants in the world that we can imagine. We don't have access to that. We only have the sampling acquired in this data set. So let's consider the data distribution versus the sampling distribution. We can just ask pandas to describe the function. We've seen this function already. So given a data frame tips and a particular column tip percentage, just give me some statistics on it. There's 244 observations. The mean of those observations is 16%. Standard deviation, the minimum, someone very rude tipped 3.6-ish%. The 75th percentile is 19.15%. So you know what that means. It means that like 75% of all of the data is less than 19.15% of a tip. Some nice person tipped 71%, and so on. So here's the code that just shows the sample distribution. So here's all the tips, and here's the distribution we see. It's pretty coarse. You can see it's a little bit tilted, so it seems to be shifted a little bit to the left. There's not too many tips of 70% or 40% and so on. This just basically shows how the tip percentage values, the actual values we observe, and the actual receipts will vary in our sample. But we want to see, does the sample means of the tip percentage vary if we keep on taking different samples from this data, from this table, in a similar way that we did bootstrapping in a previous module. So we're going to treat the existing rows, like all of the rows, we're going to pretend it's like a standard for the population, but we're just going to basically be doing bootstrapping. We're going to draw many bootstrap samples. Every sample of our data set will be of size n, which we'll specify. And my head is sized too big, so I'm going to zoom out using my Linuxy thing. There you go. And then we're going to compute the mean for each of our samples of size n. And here's all it is. We have our random number generator with a particular number for consistency. We're going to do 5,000 experiments, like 5,000 bootstrapping samples. I think you know what's going on here. There's not very much I have to do, except here's where we take our sample. We're going to sample with replacement, so we don't run out of data points very quickly. Through this experiment. We're going to, every sample we have, we're going to look at all the tip percentages and just acquire the mean, and then just keep on storing the mean in this ever-growing list over here, and then we're going to return the ever-growing list that we're adding the means to. This takes a value n as an argument, so I'm going to try it with 5 samples, every sample is going to have 5 elements in it, or 30 elements, or 100 elements in it. And each time I'm going to take 5,000, subsets, and every subset is going to be sized n, 5, 30, or 100. I want to see if there's any difference based on how big those samples are. So this is what I see. If I take only 5 receipts per sample, then I can look at the mean tip percentage. Like within each sample of 5, I compute the mean, and then I store that in my array, and then I visualize it. Nothing fancy happening here. Okay, I have 3 subgraphs here, which is this little for loop over here, and each one will be, like the first one will be the example where I'm taking 5 observations at a time, then 30 observations at a time, then 100 observations at a time. And there's not much more to explain here. I mean, obviously, if I if I have more samples here, like the numbers go up. Generally, I'm just kind of growing this, upwards, but the mean tip here is more or less stable. So usually the mean of the means anyway, I should say, is around 15% in each case. I'm just doing a qualitative analysis. This is my first observation. All of these distributions are centered more or less around the same spot. They seem to be getting narrower, at least relatively. Like I know even absolutely. So the first one ranges from 10% to over 20%, but gradually we get tighter and tighter distributions. And overall, it seems to be more and more normal shaped. I'm more confident that this is a normal distribution as opposed to this one on the left, which is a little bit coarse. I want to introduce the null hypothesis and a few other things. I'm going to check Emacs for a second and see if I'm wanting to explain anything else here that's hidden. 32. You're going to be very excited while I'm looking at my actual source for this thing. Yeah, okay, so like I was worried that there's something hidden down here, but there's nothing. So the null hypothesis we call H0, 0 for null. This is like a very popular thing. It's kind of like a straw man. This is sort of the thing that scientists set up that we kind of want to disprove. This is like a baseline claim that we more or less assume for the sake of argument. And not so secretly, this is what a lot of researchers and scientists are trying to disprove. It's very important that we not set up the null hypothesis to be a real straw man. Like a straw man argument is a logical fallacy. It's wrong. And so the null hypothesis, even though kind of it's something we wish wasn't true, we have to be as careful as we can be to set it up to be a realistic, valid, hard to beat hypothesis. Okay? Because if it's too easy, then any conclusion, if it's too easy to beat, if it's too easy to prove that the null hypothesis is wrong, then we've cheated in some sense. We've taken a shortcut. So an example of a null hypothesis might be that a coin is fair, right? So we have a coin. We want to test whether or not it's a fair coin or whether it's tilted in some way. So the null hypothesis is just that there's no weirdness going on here. So the coin is fair. Another example might be that there's no difference in the disease with and without the medicine. So imagine you're part of a team that's developed a new type of medicine, and you want to show that giving the medicine to patients will help them reduce their disease symptoms. So rather than come up with all these positive reasons why you think your drug works, again, not to sound too cheesy, but the way that science works is that we try to disprove another hypothesis, and we try to come up with ways to find faults. And if increasingly we can't maintain the null hypothesis, then we might choose another one, which I'll get to in a second. So in this case, the null hypothesis will be there's no difference. If you have the medicine, if you don't have the medicine, the results are going to be the same thing. Okay? And we're going to see if that's true or not. The alternative hypothesis, H sub 1, is kind of the opposite. So this is what we'd suspect if the opposite were true. So if the coin is not fair, like it's not going to have a probability of 50% for heads to come up. I switched the examples here. If dinner tips are actually larger than lunch tips, that would be the alternative hypothesis to dinner tips and lunch tips are the same. Or it could be, no, this medicine actually results in a observable change in the disease for the patients, would be the alternative hypothesis. Again, we're not going to go and seek evidence that the alternative hypothesis is true. We're going to set up a very hard to beat null hypothesis and then prove that that is not true. The t-statistic T, there's lots of things you can use here. This is a number that summarizes the evidence in the data. This can be the number of heads. We're going to see an example of this in a second. We're not going to get too deep into distributional measures like the t-test, the z-test, or others, but I'm just going to flag it for now. So we're going to study the sampling distribution of t, whatever the statistic is, under the null hypothesis, and then we'll make claims about it. So we have a null hypothesis. We observe some statistic, the t statistic I mentioned a moment ago. And for example, this could be the mean or a difference in means. We'll take the mean for now. Our t statistic is means. And then under the null hypothesis, we can model the sampling distribution of that statistic. You can use the CLT for this, if it makes sense, or you can do some other kind of simulation. And then you can ask how extreme is our observed statistic within this null hypothesis distribution. So a statistic that is in the far tail of the null sampling distribution could be that this means that this would be extremely rare if the null hypothesis is true. Here's a little visualization of it. So here's our test statistic Z. This can be the means computed over many, many samples, assuming that the CLT works. So again, we're computing tips, or we're computing some other thing we care about. We're computing the means in a lot of samples. We end up getting something that looks Gaussian. And then we get a new sample. We get a new mean from that sample. And we look at that mean and we say, how far away is this mean from the average of averages I've seen before? And if this mean from this particular new sample is very different than the average of averages I've seen before, then we can say, whoa, something weird is going on here. And then we can make cool claims about this new sample. So we have a null hypothesis, we have a test statistic, and then we have our observed value, t sub observed. So the p-value is the probability that if the null hypothesis were true, so again, if this thing that we assume is the case is true, what is the probability of seeing this value? That is this extreme or even more extreme. So it actually talks about a little range technically. So for a one-sided example, a p-value might be the probability under the assumption that the null hypothesis is correct, that the t-statistic is bigger than or equal to an observation. Okay, so again, we've taken many samples of some data. We look at the means in all of those samples. This gives us our nice Gaussian curve. And then we get a new sample. We compute the mean value from that new sample. That is our t observed. And then what this p-value is telling us is that looking at this t observed, what is the probability of seeing this value, this mean value, or anything bigger than it? It's called one-sided because we're looking at one side of the distribution. This is looking at a one side of this Gaussian, this little shaded area over here. I'm asking, is the for any value at t obs or bigger, what is the probability? It's basically the area under this Gaussian. So that's that. There's two-sided tests. So this looks at the absolute differences. So we take the absolute difference of the t observed and ask if the it's true of either side. So technically this test statistic is centered at 0, like I kind of hinted at before, with a standard deviation of 1. So the t statistic can be negative, like it's a lot smaller than the mean of the means. It'll be negative over here. So something like an observation that is far towards the left would be negative. I take the absolute distribution. I want to see is this very negative statistic in terms of this distribution, like way further away from the mean than I'd expect. That would be a two-tailed distribution. So again, another bit of warning, the p-value is not the probability that h sub 0 is true. A lot of scientists never think this, but a lot of undergrads or people getting familiar with these ideas sometimes think that the p-value is the probability that h sub 0 is true, and that's because they haven't internalized the idea that no, like the way that science works is not to come up with evidence or the probability that what you want to be true is true. The null hypothesis you kind of want not to be true, and the p-value you want to be small, for reasons I'll get to in a second. So again, the anti-example, some bad statements that I actually see quite often in real science. A p-value of 0.03 means that there's a 3% chance that the null hypothesis is true. This is what I just complained about. That's a bad thing to say. If the p-value is 0.01, that means that there's only a 1% probability that an observed statistic is this big or bigger. Therefore, you're going to say that you're 99% confident in your hypothesis. This is something that I worry that I myself might have said at some point. This is also not really the case. Your hypothesis has nothing to do about the Gaussian distribution, which is about the null hypothesis, which has nothing to do about your alternative hypothesis. And if you have a big p-value, so let's go back for a second. If my p-value is drawn somewhere here in the middle, then 50% of the data will be bigger than that value drawn in the middle. So p would be 0.5, and so it's a pretty big p-value. It doesn't seem very weird to me. 50% of the data will be bigger than that value. So totally normal. Totally normal in a normal sense. So that doesn't mean that there's no effect. It doesn't mean that just because you haven't found an observation that is very, very rare, that you've disproved or you haven't disproved something, you cannot claim anything. Just because this observation has a small p-value and it doesn't look particularly weird, right? So the probability of observing it is not very, very small. It doesn't mean that you've confirmed your null hypothesis. Okay, this is actually the most important one of these. You took a particular sample, you look at the mean of that sample, that particular mean doesn't look very weird. It doesn't mean that now you've proven H sub 0. You haven't done that. The p-value is about the probability of the data given the null hypothesis, not the probability of the null hypothesis given the data. So a non-significant p-value, a p-value that's very big, this observation totally looks like what I'd expect under the H sub 0, the null hypothesis. This can mean that there's a small effect. It can mean the drug actually works, or the coin is actually imbalanced. It's just hard to tell. Or it can mean that there's no effect, like maybe it actually is a fair coin, maybe the drug actually doesn't work, or it can mean that there's just not enough data. If you collected more data in that sample and you observe the mean, then the mean would shift. Like we've seen many times in previous modules, like the more data you get, the more the mean will shift as data gets more varied. And if you just got more data, then that p-value will get smaller and smaller and smaller, and then there'd be a significant effect, and then you could say something about the null hypothesis at that point. So the better phrasing here is, if there was really no difference, if there were truly no difference, results that are this extreme or more extreme than what I've observed in this new sample would only occur 3% of the time, and that's all I'm going to say, right? So it seems very rare, but I'm not making any strong claims beyond that. So we're going to go into an example of coin fairness, just for simplicity. I think this is easy to grasp. Imagine flipping a coin 20 times and you observe 17 heads. Your intuition is like something weird is going on. Like you kind of expect under normal situations, if you flip a coin n times, you expect to observe heads n divided by 2 times, so 10 times in this example. But we want to ask, is this coin, maybe it's fair, okay? That's going to be our null hypothesis. Our null hypothesis is actually that the probability of flipping heads on this particular coin is 50%. We're assuming the opposite of what we're trying to find here. We're assuming that no, there's no effect, the coin is fair. The alternative hypothesis is going to be that, okay, actually the probability of heads is something bigger than 50%. The coin is biased towards heads. And our test statistic is just going to be the number of heads we observe in a particular sample. So we're going to need the probability under a fair coin of getting 17 or more heads in 20 flips. So we can simulate that. So in this case, everything's pretty straightforward. We're going to do, in every sample, we're going to do 20 flips. We're going to do 200,000 samples. So if we do 200,000 experiments, every experiment we're going to flip the coin 20 times, and then we're going to observe how many heads we have, how many tails we have. That'll be something called a binomial distribution. I think we talked about binomial distributions at the beginning. This is a distribution with just like 2 outcomes, 1 or 0, true or false. And we're going to assume, because it's a null hypothesis, that it's 50%. So we're trying to simulate the null hypothesis as a fair coin. Sometimes we'll have a fair coin and we'll flip it 20 times, and just randomly, because of random distributions, sometimes we'll get 17 heads. Sometimes we'll get 2 heads. We don't know. Okay. And I'm just going to accumulate all these 200,000 experiments. We're going to look at all of the data, and then we're going to look at the counts in bins of 10. So head counts is a very large sample from the null sampling distribution, where t is just the number of heads. This is what the distribution looks like. So indeed, for a fair coin, this is just a regular plot, nothing fancy going on, except to have a vertical line. That's my observation. My observation is 17 heads, and I just make a dashed line over here on the right. So if I have a fair coin, 50% probability of seeing heads, and I take 200,000 samples, and every sample will have 20 coin flips in it, and I just count the number of heads in every sample. As you'd expect, the mean of these experiments is 10, and then it kind of it fades away, right? So there's still a probability here of I'm looking at maybe 1%. There's a 1% chance that flipping a fair coin will give you 15 heads and 5 tails. There's also symmetrically a 1% chance that flipping a fair coin 20 times will give you 5 heads and 15 tails. Okay, so this is what the reality would look like. It's not like if a coin is fair, then every time you flip it 20 times, you're going to get 10 heads. That doesn't make any sense. Okay, that's another conceptual leap that a lot of people struggle with, but it goes back to what we've been hammering home quite a bit in this class, which is the effect of samples. Anyway, so here's our actual observation of 17. What is the probability of actually seeing 17 heads amongst 20 flips? So we can just compute the probability. There's not much to it here. We're just looking at the actual p-value here. So what is the probability that the head counts will be greater than or equal to the particular observation we have, which is 17, and then tell me it. So the actual probability is 0.131%. So through a simulation anyway, we have the probability of observing 17 or more heads in 20 flips with a fair coin. This is very, very small. This is approximately 0.001. So you can say results this extreme, as the 17 observed heads, is or more, or 18 or 19 or 20, will only have a probability of less than 1%. So this is pretty strong evidence that this coin is not flipped. The probability of observing this under all the assumptions I've made is so small that I can throw away the null hypothesis, and then I can make a claim that actually this coin is biased in some way. This is the decision part. We have something called a significance level. This is something we set by hand. Alpha here I'm setting it to 0.05. In a lot of sciences, this is what they use. So any p-value less than 0.05 means you can throw away the null hypothesis. The coin is actually biased. The drug actually works. Dinner patrons actually tip more than lunch patrons, so you throw away the null hypothesis in each of these cases. There's all kinds of problems with this. I'm starting to get into the problematic area now. Sometimes you don't have enough samples, you don't have enough data, so you can get a p-value that is less than 5% probability, but again, you just didn't get enough data, so you happen to get a probability of 4.9%, which seems small, but it's actually could be considered fairly large under certain circumstances. So people sometimes drop this level alpha down to 0.01. So you have to get at most a 1% chance of the null hypothesis being true for you to throw it away. But if you observe an observation that is 5% or greater, you can say this is not enough evidence to reject the null hypothesis. Even if an observation is only 5% likely, that's still not enough evidence to throw away the null hypothesis. Again, this is kind of good because we're scientists. We want to be absolutely certain of something, and we're not going to just accept any advice we get. We want this level of alpha to be as small as possible. So here's a little danger thing. This is one of my favorite topics in this area of significance testing, but we're not going to get much of a chance to talk about it. I'm just going to make sure. It looks like there's something hanging off the bottom of this page, so I'm going to go to my code here and make sure nothing's down there. No, nothing's hanging at the bottom of this page, so we're fine. So suppose our null hypothesis is actually true. Okay, assume that the coin is actually fair, and we test m independent hypotheses, and we have a level set to 0.05, which means that every test has basically a 5% chance of a false positive. So the coin is fair. So it's definitely fair. We know it to be fair. But then it results in that Gaussian distribution like we saw before. And at the ends of those distributions, it'll generate diminishingly small probabilities of observing 19 heads, 20 heads amongst 20 heads. But there's still some probability, right? So what that means is there's still a chance that you generate a false positive in terms of our hypothesis. So, this fair coin, you sample it, you take 20 coin flips, you count the number of heads, it's 17, 18, or 19, you know that the chances of that happening are less than 1%, but that's actually what this fair coin actually generated. So that's a false positive. We've got a p-value that's below our level. We want to throw away the null hypothesis, but we're going to do that because of an accident of just random sampling. So this chance of getting at least one significant result by accident is this interesting formula here, which again, this is a bit of a side note, so I'm not going to test you on this really, but I think it's really interesting. It's 1 minus 1 minus alpha, and this last little bit is in the parenthesis is all raised to the power of m. Okay. If you're interested, we could sit down and talk about like why this is the case. But imagine like you're doing something over and over again, and there's a probability of something occurring every time you perform this experiment. Probabilities have to go between 0 and 1 at the absolute maximum if it's absolutely certain, so usually it's not exactly 1. So if you do lots of experiments over and over again, and the probability of seeing something typical might be very high. It might be 99%, or in this case, I'm saying 95%. Okay, so my alpha level is 0.05. So there's like a 95% chance that in a particular sample, what I observe will not look atypically weird. The p-value will be big. I'm getting samples of 10, 11, 12 heads. Everything looks good. There's a 95% chance of that. Okay, so I take a sample, I observe my p-value, and I don't throw away my null hypothesis. I take another experiment, and another sample, I compute my coin flips, I compute my p-value to see how likely what I observe is, and again, I throw away my null hypothesis with 95% probability. I do this over and over again. Well, the chances of not throwing away your null hypothesis every single time will be a function of the probability of doing so raised to the power of the number of experiments I've done. Okay, so if I only do, I'm kind of using m a couple of times here. I'm using 20 a couple of times here, so I know I'm doing 20 coin flips per sample. Now I'm doing 20 samples, and what is the probability that I will accidentally throw away my null hypothesis even when I shouldn't? Even after only just 20 experiments, this equation gives me a probability of 64%. Okay, so if you have 20 people in your team and they're all going to do their own sample of 20 coin flips, and they all get their different means or different counts of coin flips, most people will be around 10, 11, 12 because everyone has a fair coin. But one person, because of a random accident, will flip 20 times and they'll observe something like 17, 18, or 19, or I think even 16 heads, or 16 tails, and if it's two-sided. And then, yeah, there's a 64% chance that there'll be at least one person in your group of 20 friends who will see that, okay? That's a pretty high probability, right? So there's a more than 50% chance that one of your friends will raise your hand and say, hey, I found an unfair coin. But it's not unfair. It's just an accident of sampling, okay? I hope that's very clear right now, right? So this is a trap a lot of people fall into, okay? So Just because of how we've set up these experiments, there's a small chance that we'll observe something very, very weird, but it's not because of an actual effect in the data. It's an effect of the random samples. Okay, so what that means is if we do the more and more experiments we do, the more and more our value alpha needs to be adjusted. Okay, like 5% is so huge that when we plug it into this formula, and after just 20 experiments, we get this massive 64% probability that somebody will claim that a fair coin is unfair. So if you want to have a smaller alpha value, so you say alpha is 0.01, then now this 0.95 becomes 0.99. And then this overall probability goes down a little bit. But then if you do more and more experiments, then this overall probability will keep on creeping up again. So I'm not going to get to go into much more detail about this, but it's one of my favorite topics. And actually, I'll make sure I don't mention anything here. Actually, I do, so I apologize. So when I post these slides, I'll make this scrollable. Down here at the bottom of this key idea is I link to Bonferroni correction in something called false discovery rate, or FDR, not Franklin Delano Roosevelt, but they're techniques to take these experiments and then to adjust things so that if you're doing lots and lots of experiments and you're looking for the fair coin over and over again, or looking for an unfair coin over and over again, you can make the requirement for extra evidence extremely stringent, right? By basically just lowering and lowering this level of alpha as a function of the number of experiments you're doing. Okay, so again, super important stuff in reality, not so much in first year, but definitely in third, fourth year in grad studies and beyond. So just to wrap things up a little bit, the central limit theorem versus a simulation. So there are two ways to get p-values. One is through direct simulation, like we just did. We just do a random simulation of coin flips under an assumption that something is fair, under the null hypothesis. Very flexible. We can set things up the way we want. We can represent things visually like we did, and it's it can be computationally expensive. We're not going to talk too much about Monte Carlo methods in this course either, but you can set up pretty complicated experiments that can be very hard to run. In real life, we don't do that. In real life, we gather lots of real data, like the TIPS database actually, and then we want to run many samples. We want to compute, means of means, like we talked about earlier. We want to compute the central limit theorem. And then if that's the case, then we have all these other tests available to us that can basically get us p-values. Given all these data I've observed, what is the chance of seeing this particular thing? And again, we're not going to have a chance to talk about that in this class, but you're going to hear about the t-statistic, I'm sure, especially if you're doing other sciences. It's a very easy gateway into significance testing, but it's also easy to misuse because it has so many assumptions built into it. So I just wanted to build some intuition about p-values and what they represent and how they relate to the null hypothesis. Often they lean on standard distributions or normal distributions. We may come back to that later in this course, but unlikely. Again, communication is so crucial. We just talked a lot about communicating results in a recent cluster of modules. We always want to state the question and null hypothesis extremely transparently, clearly, and fully, and early. We don't want to keep on going back to our null hypothesis and changing things if our observations don't match what we like. We want to report the statistic we're using, so like the mean, the difference in means, and so on. We want to look at the observed values of its estimate under uncertainty. This might be standard error, like we had in a quiz recently. It could be confidence intervals. If it's p-value, then we also want to talk about the significance level. We can't just compute the p-value and say that the null hypothesis is wrong. We have to say, under the significance level of alpha being 0.01, this is the p-value we get in our observation. The p-value is smaller than the significance level. The chances of the null hypothesis being true is so small that we can throw it away. When you interpret things in plain language, this is really hard, and I imagine I sometimes fall into the traps of saying things a little bit incorrectly. When you throw away the null hypothesis, it's sometimes you might say there's no effect. When you don't throw in the null hypothesis, see, I'm doing it right now. When you have a p-value that is too big, you might be tempted to say, like, okay, there's no effect of this drug, right? The probability of observing what we see in this patient group is what we'd expect to see if the drug didn't work, therefore the drug doesn't work. But that's not true. We can't, just because the p-value is big, doesn't mean we've confirmed the null hypothesis. The whole point of this is that we're trying to disprove things, right? So if the p-value is big, we can't clap our hands and say the h sub 0 is confirmed. We just didn't find enough evidence we did not find enough evidence to throw away the null hypothesis. It doesn't mean the null hypothesis is true. And then this can also have an effect on our practicality. So is our effect we've observed, like the p-values or stats related to it, which we didn't get into, does it matter in the real world? Like, we talked about coin flips here, but if it's drugs, or if it's tips and you work at a restaurant, or whatever the statistic is you're looking to run, like what kind of decisions can be made? That's always the important thing. And who are you communicating this to? Are you communicating p-values to doctors who've probably seen lots of statistical tests? Are you conveying it to people in other disciplines who might not have been educated in statistical tests? That matters, of course. There's all kinds of ethics incursions here. So you might have heard of things called p-hacking. This is something I really don't like in the statistics of actual publications. A lot of papers will only, or journals or conferences will only publish research papers when the p-value is less than some predetermined level, like 0.05. So first of all, where does this level come from? It's usually just drawn out of thin air. It doesn't mean anything, so that by itself is annoying. Like these people having this gateway, which doesn't mean anything really, is annoying. But more importantly and more annoying to me is, like, I think behind the scenes, again, like there's a little bit of paranoia here, but there's also some studies that I can link to if you want that show that people do this, that people will keep on running experiment after experiment after experiment and getting more and more samples, and not doing the kinds of corrections I mentioned because of repeated sampling, until they finally find a sample in which they can throw away the null hypothesis, and they can say, look, in the sample, the p-value is very small, the null hypothesis must be false, therefore my drug or my intervention must work, give me a Nobel Prize or whatever it is, or at least get my paper published. That happens an awful lot, right? So we haven't talked too much about machine learning and test distributions and training distributions, but like if you're kind of doing a test and then seeing something you don't like and then going back and then fiddling with things until you get the result you want, that's not good science. That's performative science. You're putting on a white lab coat and pretending to be a scientist, but you're not a real scientist. At least not in that moment. This results in the replication crisis. I should link to some papers here. I'll try to remember to add some links here. But yeah, like often things will be published with p-values that are very small. Another person will get another sample of data from their own lab to try to recreate what was done before, but of course they can't because that sample that was used to get this very small p-value is like cherry-picked, so they can't replicate something. That paper was bad. And then, yeah, any kind of biases or confounding, like we talked about earlier, hide behind these p-values. It's better to pre-register your hypotheses and analysis plans, make it open, or get other people to test things for you as opposed to running all the analyses in your lab yourself. We don't talk about effect sizes or confidence intervals now. We talked about confidence intervals earlier, so like don't just report p-values, report tons of statistics as much as possible, and be transparent about everything, data collection, exclusions, number of tests performed, and so on. In technology, we tend to do A/B testing, so we tend to have two versions of the same website or two models we're comparing against each other, and we want to see if there's an effect, if there's a difference. So we have one machine learning model which your competitors made, and you have your machine learning model which you spend a lot of time on. Is your model actually better than theirs? I wish I could spend more time talking about this, but yeah, you'd basically do something like a p-value. You'd do some experiments. You'd take a lot of measurements. You'd compare the means of those measurements, and if the mean in a particular test case shows a significant improvement in your model over someone else, then and only then would you make a claim about your model being the state of the art. And of course, that's not what happens in practice, although it should, and people know better. Clinical trials, p-values come up an awful lot. Clinical trials are usually set up very well, and they usually have an idea of doing these tests well to begin with. Policy and government, does a certain policy reduce wait times in a hospital? Does it reduce disparities? If you're working at a government, you're going to see statistics of this type all the time, and either in sampling or in measurement from actual data. Later in this class, we'll talk about null models and power. So what is the probability of looking at real effect? This is actually going to be one of your lab modules. And then actually in the next theory module, we'll talk about causal thinking, and we'll go back to correlations and what is the difference between correlation and causation. As always, here's your quick check, which are good to do. It's a pleasure as always. Thanks for watching. See you next time.